Okay, so multicollinearity. In econometrics, one important assumption when we consider multiple linear regression model is multicollinearity. There is no multicollinearity. When we consider the classical linear regression model with more than one variable, more than one x variable, we consider that there is no collinearity, multicollinearity between two x variables. That means there is no collinearity between x1 and x2 or x1 and x3, or it can be x1 and xn. So the assumption 10 of the classical linear regression model is that there is no multicollinearity among the regressors, that means x variables, included in the regression model. In this chapter, we take a critical look at this assumption by seeking answer to the following questions. The first question is, what is the nature of multicollinearity? Is multicollinearity really a problem? What are its practical consequences? How does one detect it? And what remedial measures can be taken to alleviate the problem? So we will consider 5 main questions. One is, what is the nature? Is it really a problem? If it is a problem, what are its practical consequences? How can someone detect it? How can someone know that there is a multicollinearity? And the last one is very important. What are the remedial measures that we can take to alleviate this problem? First, we will go with the nature. The term now, the term multicollinearity means the existence of a perfect or exact linear relationship among some or all explanatory variable of a regression model. Let's say for the k variable regression involving an explanatory variable x1, x2, xk, an exact linear relationship is said to exist if the following condition is satisfied. So that means that if this condition satisfied, where lambdas are the parameters constants, if this condition satisfies, that is lambda 1 x1 plus lambda 2 x2 plus lambda k xk is equals to 0, then we will consider that there is an exact linear relationship between the explanatory variables. However, the term multicollinearity is used in a broader sense to include the case of perfect multicollinearity as shown in equation 1. So the equation 1 is basically shows the perfect multicollinearity, as well as the case where the x variables are intercorrelated but not perfectly, so that there is some error term or there is some term vi which leads to the equation becomes 0. Okay. So where vi is the stochastic error term. That means from equation 1 we can clearly say that there is a perfect multicollinearity. Whereas from equation 2 we are not clearly saying that there is a perfect multicollinearity, rather we can say there is some multicollinearity. So there can be two types of multicollinearity, one is perfect and another one is not perfect, but there is multicollinearity problem. The next important question is, what are the several sources from which multicollinearity may occur? Some are as follows. The first source from which the multicollinearity can occur is while doing the data collection method. The data collection method employed, for example, exactly, ভিআইটা ইনক্লুড করলে ইমপারফেক্ট থাকছে আর ভিআইটা না থাকলে পারফেক্ট থাকছে। এবার আমরা আসছি সোর্সেস গুলোতে। ফার্স্ট প্রবলেমটা হতে পারে যদি আমাদের অবজারভেশনস গুলো অনেক লিমিটেড থাকে। যদি লিমিটেড জায়গা থেকে অবজারভেশনস নিই তাহলে মাল্টিকোলিনিটি প্রবলেম থাকতে পারে। So the data collection method employed, for example, sampling over a limited range of the values taken by the regressors in the population. The second problem is constraint on the model or the population being sampled. For example, in the regression of electricity consumption on income and house size, there is a physical constraint in the population in that families with higher income generally have larger homes than families with lower incomes. For example, it means that when we are regressing the electricity consumption on income and house sizes, that means that income and house size are the explanatory variable. Income and house size টা তোমার explanatory variable আর electricity consumption টা ধরে নাও y variable. তাহলে তুমি দেখতে চাইছো যে ইনকামের উপরে ইলেকট্রিসিটি কনজাম্পশনের কি এফেক্ট থাকতে পারে বা হাউস সাইজের উপরে ইলেকট্রিসিটি কনজাম্পশনের কি এফেক্ট থাকতে পারে। তাহলে আমরা এটা বলতে পারি যত হাউস সাইজ বেশি অত ইলেকট্রিসিটি কনজাম্পশন বেশি, আবার অন্যদিকে এটাও বলতে পারি যে ইনকাম বেশি হলেও ইলেকট্রিসিটি কনজাম্পশন বেশি হতে পারে। But there is a problem. The problem is income and house size may be related. The families with higher income tend to have larger homes, right? তাহলে এখানে কিন্তু আমি যদি পার্শিয়াল এফেক্ট গুলো দেখতে চাই দেখতে পারবো না, জাস্ট বিকজ ইনকাম এন্ড হাউস সাইজ মে বি রিলেটেড। So this is the problem. Second is the model specification. For example, adding polynomial terms to a regression model, especially when the range of the x variables is small, তখন একটা প্রবলেম আসতে পারে। যদি আমরা রিগ্রেশন ইকুয়েশনটা হয়তো লগারিদমিক টার্মসে আছে বাট আমরা রিগ্রেশনটা লিনিয়ার টার্মসে নিলাম, তখন কিন্তু প্রবলেম আসতে পারে। The last one is যদি মডেলটা আমরা ওভার ডিটারমাইন্ড করে ফেলি। এটা তখনই হয় যখন মডেলে অনেকগুলো বেশি এক্সপ্লেনেটরি অবজারভেশন ভেরিয়েবলস আছে দেন দ্য নাম্বার অফ অবজারভেশনস। মানে এক্স ভেরিয়েবলস গুলো অনেকগুলো, নাম্বার অফ অবজারভেশনস থেকে এক্স ভেরিয়েবল গুলো অনেকগুলো। This could happen in medical research when there may be a small number of patients about whom information is collected on a large number of variables. কিছু পেশেন্টস দেরই তুমি ইনফরমেশনস কালেক্ট করছো, বাট ইনফরমেশনটা যেটা তুমি কালেক্ট করছো ওটা অনেকগুলো ভেরিয়েবলস এর উপরে, তখন কিন্তু মাল্টিকোলারিটি প্রবলেম আসতে পারে। An additional reason for multicollinearity, especially in time series data, may be that the regressors included in the model share a common trend, that is they all increase or decrease over time. That means that if we take inflation and if we take unemployment, and as we know from the Phillips curve there is a relationship between inflation and unemployment, and with the time series data in hand we can see that relation, and if we want to see the effect of inflation and unemployment on GDP growth, that can be a misleading, where because inflation and unemployment can be related, right? Thus in the regression of, for example, thus in the regression of consumption, expenditure on income, wealth and population, the regressors income, wealth and population may all be growing over time. Income, wealth, population সবগুলোই একসাথে বাড়তে পারে at more or less the same rate, that can lead to a collinearity among these variables. That means that তাহলে আমরা কেন ক্লাসিক্যাল লিনিয়ার রিগ্রেশন মডেল যখন আমরা পড়েছিলাম তখন আমরা কেন ধরে নিয়েছিলাম যে কোন রকমের মাল্টিকোলিনিয়ারিটি নেই? তার কারণটা হচ্ছে যদি মাল্টিকোলিনিয়ারিটি থাকে তাহলে কিন্তু আর আমরা বিটা 1 বিটা 2 কে আমরা বের করতে পারবো না। কিভাবে আমরা আসছি, why it is so we will come in the next paper, মানে next পার্টেই বুঝতে পারবো। If multicollinearity is perfect in the sense of equation 1, যেটা আমরা আগে দেখলাম, যদি পারফেক্ট মাল্টিকোলিনিয়ারিটি থাকে কোনো এরর টার্ম নেই, then the regression coefficients of the x variables are indeterminate and their standard errors are infinite. Why? We will come, just give you a minute. If multicollinearity is less than perfect, that means imperfect, as in equation 2, the regression coefficients, although determinate, possess larger standard error, which means that the coefficients cannot estimate with great precision or accuracy. এইটাকে আমরা এবার demonstrate করব। These facts can be demonstrated readily in terms of three variable regression model. আমরা আবার আগের মতোই three variable regression model এ আছি, খুবই সিম্পল ফর্মে আছি। Using the deviation form where all the variables are expressed as deviation from their sample means, we can write the three variable regression model as we know that this is the three variable regression model equation. Yi equals to beta 2 hat small x2y plus beta 3 hat small x3y plus ui hat. This is my equation 3, right? We know that when we take regression equations in the deviation form, the beta 1 hat term get cancels out, the intercept term gets cancelled out, right? Now we also understood in the previous class that from unit 2 that beta 2 hat looks just like this, summation of small yi x2y times summation small x3i square minus summation of small yi x3i times summation of small x2y into x3i whole divided by summation of small x2y square summation of small x3i square minus summation of x2y x3i whole square. Similarly, we have beta 3 hat where all the terms are in the deviation form. Now, let's say that we have a relationship in the x3 and x2 variable where we are assuming that x3i equals to lambda x2i, যেখানে ল্যামডাটা একটা নন জিরো কনস্ট্যান্ট। যদি তাই হয় যে x3i equals to lambda x2i হয়, তাহলে আমি ইকুয়েশন 4 এ x3i জায়গায় lambda x2i বসাতে পারি। যদি বসাই তাহলে আমার বেসিক্যালি কি হবে, উপরে ল্যামডা স্কয়ার সামেশন অফ x2i স্কয়ার হয়ে যাবে, তাই না? আর সিমিলারলি এখানে সামেশন অফ, আচ্ছা এইখানটা এখানটা x2i হবে, তাই না? বিকজ x3i টা x2i হবে। তাহলে দেখতে পাচ্ছ যে উপরের নিউমারেটরের সবগুলো টার্মস বেসিক্যালি কেটে যাচ্ছে, তার মানে বেসিক্যালি 0/0 হয়ে যাচ্ছে, তার মানে সেটা ইনডিটারমিনেট, তাই না? That means that if there is a perfect multicollinearity, then we cannot actually get the value of beta 2 hat. এবার next আসছি যে why do we obtain the result shown in equation 6? Recall the meaning of beta 2 hat. What is meaning beta 2 hat? আমরা আগের দিনও পড়ে এসেছিলাম, it is the average change or it is the change in the conditional mean value of y for a given change in the value of x. It gives the rate of change in the average value of y as x2 changes by a unit holding x3 constant. We assumed that x3 is constant when we are interpreting beta 2 hat, right? That's why it is known as partial coefficient, regression coefficient. But if x2 and x3 are perfectly collinear, then there is no way x3 can be kept constant. Because if x2 changes, x3 will change by a factor lambda as far as our assumption is concerned. So what it means then is that there is no way of disentangling the separate influences of x2 and x3. We cannot separate it. We cannot separately see the influence of x2 and x3 on y. That means that for practical purposes, x2 and x3 are indistinguishable. They are inseparable. In applied econometrics, this problem is most damaging since the entire intent is to separate the partial effects of each x upon the dependent variable. So that leads to the main problem. Clear? Okay. Now, to see this differently, এটাকে আমরা একটু অন্যরকম দেখছি। সাপোজ আমরা ধরে নিলাম যে x3i equals to lambda x2i in equation 3. equation 3 টা কি ছিল দেখো একবার, ডেভিয়েশন ফর্মে এটা ছিল। এবার যদি আমি x3i equals to lambda x2i পাই, তাহলে আমি বাইরে ল্যামডাটা নিয়ে আসবো, তাহলে বেসিক্যালি আমরা কি পাচ্ছি, আমরা পাচ্ছি yi equals to beta 2 hat x2i plus beta 3 hat lambda x2i লিখতে পারবো in place of x3i. So what we are getting is that yi equals to beta 2 hat plus lambda beta 3 hat times whole bracket times x2y plus ui hat. Now in place of beta 2 hat plus lambda beta 3 hat, we can write alpha hat, because beta 2 hat plus lambda beta 3 hat all are constant, so we can easily write lambda hat, right? That means what we actually got is basically a linear regression model with one variable, one explanatory variable, yi equals to lambda hat x2i plus ui hat. We can use easily, using OLS formula, ordinary least square formula, we can easily get the value of alpha hat, which is we know as alpha hat equals to summation of x2i yi whole divided by summation small x2y square. That we all know. This is the regression coefficient. That means what we are getting is one equation where beta 2 hat equals to lambda beta 3 hat equals to summation of small x2y yi by summation of small x2y square. This is only one equation with two unknowns, beta 2 hat and beta 3 hat. And we know that if we have two unknown variable and one equation, we cannot get the values of beta 2 and beta 3. There cannot be any unique value of beta 2 and beta 3 hat. There can be infinite solutions, right? For example, if I say x plus y equals to 20, we cannot easily get unique value of x and y. This is only one linear equation with two unknowns. Okay. Therefore, although we can estimate alpha uniquely, there is no way to estimate beta 2 and beta 3 uniquely. Mathematically, alpha hat equals to beta 2 hat plus lambda beta 3 hat. It gives us only one equation in two unknowns. And there is infinite solutions for given values of lambda and alpha hat, right? There can be infinitely many solutions. So the upshot of the preceding discussion is that in the case of perfect multicollinearity, one cannot get a unique solution for the individual regression coefficients. We cannot get the values of beta 2 hat and beta 3 hat uniquely. But notice that one can get a unique solution for linear combination of these coefficients. We get one solution alpha hat. So the linear combination alpha hat equals to beta 2 hat plus lambda beta 3 hat is uniquely estimated by alpha, given the values of lambda. In economic literature, a function such as beta 2 hat plus lambda beta 3 hat is known as estimable function, because this is estimated but we cannot get the value of beta 2 hat and beta 3 hat uniquely. Okay. So this perfect multicollinearity is some kind of extreme case, just like perfect competition or a monopoly. This is some kind of pathological extremes that actually do not hold in reality. Okay. So the perfect multicollinearity situation is a pathological extreme. For example, in a market structure, when we assume that there is a perfect competition or monopoly, these are the extreme phenomena which does not actually hold in reality. Perfect competition and monopoly are just classical assumptions, classical model, right? Next, we try to, just because the reality is very complicated, we cannot estimate reality. So we assume certain phenomenon and we try to see how much the reality is different from the natural part, normal part. Just like normal distribution, nothing is normally distributed, right? So the perfect multicollinearity situation is a pathological extreme. Generally, what we see is that there is no exact linear relationship among the x variables, especially in data involving economic time series. Here, thus, turning to the three variable model in the deviation form given in 3, instead of exact multicollinearity, we may have some kind of not so perfect linear relationship, which is x3i equals to lambda x2y plus vi, where lambda is not equal to 0 and vi is the stochastic error term. And we know that if it is a stochastic error term, by assumption we can say that summation of x2i vi is not equal to 0 as far as our assumption is concerned. We know that there should not be any correlation between the explanative variable and the error term, right? Or we can also say that this is the second normal equation, right? Summation of x2i vi equals to 0. মনে করে দেখো normal equation যেটা পার্টটা, হ্যাঁ. So in this case, the estimation regression coefficient beta 2 and beta 3 may be possible, just like the previous case. We have summation of yi x2y whole times lambda square summation x2y square plus one extra term which is summation of vi square minus lambda summation yi x2y plus summation of yi vi whole times lambda summation x2y square whole divided by summation x2y square times lambda square summation x2y square plus summation vi square minus lambda summation x2y square whole square. A similar expression can be derived for beta 3 hat, which we have not written, but there we can easily derive it. But unlike equation 6 where we are getting 0 by 0 form, this is not 0 by 0, right? So unlike equation 6, there is no reason to believe a priori that the previous equation 7 cannot be estimated. This can be estimated. Okay. But what we actually have seen that this can be estimated, beta 2 hat can be estimated, but we know that the variance will be much higher, right? Because there exists some error term as well. So variance will be much higher. If the variance is higher, we cannot do other things like t statistic or f test. We cannot do because the critical region gets increased, right? So there can be some kind of problem of types of error, type 1 error and type 2 error, right? So now what are the practical consequences of multicollinearity? If we have multicollinearity, what are the practical consequences? In case of near or high multicollinearity, if not perfect, one is likely to encounter the following consequences. First, although blue, it is blue. Blue means it is best linear unbiased estimator, but it is not MVUE. It is not minimum variance unbiased estimator. But the OLS estimators have larger variance and covariance and making precision estimation difficult. Because of the consequence 1, the confidence interval tend to be much wider, right? The confidence interval will get increased because we know that in the confidence interval there is a term of variance. So if variance increase, the confidence interval will get increased, right? So this will lead to the acceptance of zero null hypothesis more readily. We are accepting the zero null hypothesis more readily. That can lead to kinds of error. Also, because of the consequence 1, the t statistic, the t ratio of one or more coefficients tends to be statistically insignificant. Although the t ratio of one or more coefficient is statistically insignificant, R square, the overall measures of goodness of fit, can be very high, right? R square can be very high. The OLS estimation and their standard errors can be sensitive to small changes in the data. The OLS estimation and their standard errors can be sensitive to small changes in the data. If the data changes to just a insignificant amount, the OLS estimation and their standard errors can get increased. So to see the large variance and covariance, recall from unit 2 the variance and covariance of beta 2 hat and beta 3 hat. We know that the variance looks like this, right? Variance of beta 2 hat equals to sigma square by summation x2 square whole divided by 1 minus r square 2 3, right? Where r square 2 3 was the correlation coefficient. Clear? And similarly, variance of beta 3 hat looks like this, sigma square by summation of x3 square times 1 minus r square 2 3, where correlation coefficient r square 2 3 is just given in equation 8. And similarly, the covariance will be like this, that we have understood in the previous lecture. Okay. Now, it is apparent that if r square 2 3 increases, then 1 minus r square 2 3 will get decreased, right? So if 1 minus r square 2 3 get decreased, that means in the denominator we are getting a small number. That means the ratio will get increased, right? Denominator যদি কম নাম্বার থাকে রেশিও তো বাইরে বেড়ে যায়, তার মানে ভেরিয়েন্সটা বেড়ে যাচ্ছে. So it is apparent from equation 7 and 8 that as r square 2 3 tends towards 1, that is as collinearity increases, the variances of the two estimators increases, and in the limit when r square 2 3 equals to 1, they are infinite. Why? Because if r square 2 3 is 1, that means 1 minus 1 is 0, something by 0 is infinity, right? That means if there exists perfect multicollinearity, then the variance of beta 2 hat will be indeterminate. So it is equally clear from equation 9 that as r square 2 3 tends towards 1, the covariance of two estimators will also increase in the absolute value. The covariance between beta 2 hat and beta 3 will obviously increase in the absolute value because r square 2 3 is in the numerator of equation 9. Clear? So now to detect the multicollinearity, we use variance inflation factor. Very important. This may come in your exam. What is VIF? If you see the past year questions, you will get this question. What is variance inflating factor? So the speed with which variance and covariance increase can be seen with the variance inflation factor, which is basically VIF equals to 1 by 1 minus r square 2 3. Okay. So if r square 2 3 increases, then 1 minus r square 2 3 will decrease. That means 1 by 1 minus r square 2 3 will get increased, right? So if there is a high collinearity between x2 and x3, then the VIF will get increased. Then we'll get high VIF. And obviously in a limit, if r square 2 3 is equals to 1, then VIF will approach infinity. So VIF shows how variance of an estimator is inflated by the presence of multicollinearity. What VIF shows is that how much the variance of the estimated term gets inflated, gets increased by the presence of multicollinearity. Clear? VIF shows that how much variance of the estimator can get increased by the presence of multicollinearity. At limit, as r square 2 3 approaches 1, the VIF approaches infinity. That is, as the extent of collinearity increases, the variance of an estimator increases, and in the limit it can becomes infinity. As can be readily seen, if there is no collinearity, that means x2 x3 gets 0, then VIF will be 1. Right? So using this definition per se, we can express equation 7 and 8 as this. Right? Can we express this equation? Because we know that variance of beta 2 hat is equals to sigma square by summation of small x2 square times 1 minus r square 2 3. And since 1 by 1 minus r square 2 3 is BIF, we can easily write variance of beta 2 hat equals to sigma square by summation x2 square times VIF. That means if VIF increased, then variance of beta 2 hat will increase, which shows that variances are directly proportional to the term VIF. The result just discussed can be extended easily to the k variable as well. In such a model, the variance of the kth coefficient can be expressed as follows. Right? Variance of beta high equals to sigma square by summation of xj square whole times 1 by 1 minus r square ij, where beta j is the estimated partial regression coefficients of regression xj, r square is the regression of xj on the remaining k minus 2 regressions, and summation of xj square is summation of xj minus x bar j whole square. So we can also write the equation 11 as variance of beta high equals to sigma square by summation of xj square times VIFJ. As we can see from this equation that variance of beta I is proportional to sigma square and VIF, but inversely proportional to summation xj square. Obviously it will be inversely proportional, because if the deviations in the explanatory variable get increased, then the variance will obviously decrease. That means if there is a thus whether variance of beta I is large or small will depend on these three ingredients. Before proceeding further, it may be noted that the inverse of VIF, if the inverse of VIF is nothing but the tolerance level, TOL or the tolerance. That means 1 by VIF is defined as tolerance in econometrics, which is basically 1 minus r square j. That means if r square increase, the tolerance level gets decreased, right? So when r square j is equals to 1, the tolerance level is 0, and when r square j equals to 0, then the tolerance level is 1. Clear? So because of this intimate connection between VIF and tolerance, one can use this term interchangeably. Now, to detect multicollinearity, we have some rule of thumb. The VIF can be used as an indicator of multicollinearity. The larger the value of VIF, the more collinear the variable xj. That means to check whether there is a multicollinearity problem in our regression model, we need to understand, we need to get the value of VIF. If VIF is very high, that means there is high collinearity, which is a very big problem. But if VIF is very small, then there is not so much exact linear relationship between the explanatory variables, and that is not that much a big deal. So the larger the value of VIFJ, the more collinear the variable xj. As a rule of thumb, if VIF of a variable exceeds 10, if the variance inflating factor exceeds 10, which will happen if r square j exceeds 0.90. Clear? Because we know that VIF is 1 by 1 minus r square j. So if r square j is 0.9, that means if the correlation coefficient is 0.9, That means 1 by 1 minus 0.9 means 1 by 0.1, which is 10. Right? So if VIF exceeds 10, then it is said to be high collinear. Right? Of course, one could also use tolerance J as a measure of multicollinearity in view of its intimate connection with VIF. Obviously, the closer the tolerance to 0, the greater the degree of collinearity of that variable with the other equations. That means if tolerance level tend towards 0, that means there is a high collinearity, and if the tolerance level tend towards 1, then there is low collinearity. On the other hand, the closer tolerance level is 2, the greater the evidence that xj is not collinear with the other equations. X to 1 hobe, tolerance level is to 1. Next, if there is a multicollinearity problem and we are হ্যাঁ আসতে পারে, ঠিক আছে, হ্যাঁ ডিরেক্ট বার করতে বলতে পারে বা ডিরেক্ট কোশ্চেনস দিতে পারে। আচ্ছা, ওকে। Now, if we have after our doing our regression, if we see that VIF is very high, then that means there is a multicollinearity problem. Now the next step is what are the remedial measures, how we can solve it. হ্যাঁ বুঝতে পারলাম যে ভুল হয়ে গেছে, এবার সলভ করব কি করে, that is the main problem. So first is a priority information. Suppose we consider the model yi equals to beta 1 plus beta 2 x2y plus beta 3 xgi plus uy, where y is the consumption, x2 is income, and x3 is wealth. As we noted before, income and wealth variables tend to be high collinear. We know by economic ideas, by economic sense, we can also say that the variable income and wealth can be correlated. But suppose a priori we believe that, if we believe that the correlation is something like beta 3 is 0.10 times beta 2, that is the rate of change of consumption with respect to wealth is 1/10 the corresponding rate with respect to income. If we have this priority information in hand, we can then run the following equation, right? We will not do the basic regression, rather we will do this one, where yi equals to beta 1 plus beta 2 x2y plus beta 3 x2i plus 0.10 beta 3 x3i plus uy. That means that beta 1 plus beta 2 x2 xi plus uy, where obviously xi now becomes x2i plus 0.10 x3i. Clear? Now if we obtain from this, we can readily obtain beta 1 and beta 2 hat, right? So once we obtain beta 2 hat, we can easily estimate beta 3 from the postulated relationship, that is beta 3 equals to 0.10 beta 2, right? So if we have some priority information, we can easily use it to get the values of beta 2 and beta 3. So how does one obtain a priority information? It could come from previous empirical work in which the collinearity problem happens to be less serious, or from the relevant theory underlying the field of study. For example, there is a collinearity between income and wealth, as generally in the case in most sample data. Such a transformation may reduce or eliminate collinearity problem. Okay. The second that we can do is to by combining the cross-sectional and time series data. A variant of the extraneous or a priority information technique is the combination of cross-sectional and time series data, known as pooling the data. So if there is a multicollinearity problem, we can pool the data and can run the regression equation. There, by this way, we can to some extent can solve the problem of multicollinearity. The third that we can obviously do is by dropping some variables. This is the most simplest idea. Drop some variables. If we know that there is a relationship between income and wealth, drop any one. Right? So when faced with severe multicollinearity, one of the simplest thing to do is to drop one of the collinear variables. Thus, in our consumption income wealth illustration, we can drop the wealth variable, but in dropping a variable from the model, we may be committing a specification bias or specification error. Why? Because we are, by our own hand, we are eliminating something, some information, which may be important in our research work, but we are in our own hand doing some kind of work which can obviously affect my regression equation, which can affect my research. Specification bias arises from incorrect specification of the model used in the analysis. Thus, if economic theory says that income and wealth should be both included in the model explaining the consumption expenditure, dropping the wealth variable can constitute specification bias. Clear? Fourth is to transform the variables. Suppose we have time series data on consumption, expenditure, income and wealth. One reason for high multicollinearity between income and wealth in such data is that over time both the variables tend to move in the same direction. We know that in the time series data income and wealth can move in the same direction. One way of minimizing these dependencies is to proceed as follows. If the relation is given as yt equals to beta 1 plus beta 2 x2t plus beta 3 x3t plus ut, where t denotes the time period. Okay? So if this is my regression equation 1, if we use 1 lakh time period, that is yt minus 1 year before, yt minus 1, then we can easily write this as beta 1 plus beta 2 x 2t minus 1 plus beta 3 x 3t minus 1 plus ut minus 1. That means suppose we are using regression equation for 2010 and 2011. Now if we subtract it, yt minus 1, that means if we subtract equation 1 from equation 2, you will get equation 3, right? This is known as first difference. This is known as first difference. Equation 3 is known as the first difference form because we run the regression not on the original variables but on the differences of successive values of the variables. By doing so, we can eliminate some kind of multicollinearity. Okay? Because due to time series data, there is a collinearity, and we are doing this first difference to counterattack the problem. So the first difference regression model often reduces the severity of multicollinearity because although the levels of x2 and x3 may be highly correlated, there is no priori reason to believe that their differences will also be highly correlated. Okay? This means that though the first difference regression model often reduces the severity of multicollinearity, it reduces the severity because although x2 and x3 may be highly correlated, there is a priori reason to believe that their differences may not be highly correlated. Another commonly used transformation in practice is the ratio transformation, which is if we have yt equals to beta 1 plus beta 2 x2t plus beta 3 x3t plus ut, where y is the consumption expenditure, x2 is GDP, x3 is total population, let's say. And we know that with time GDP and population both can increase. Okay? So since GDP and population grow over time, they are likely to be correlated. One solution to this problem is to express the model on a per capita basis. That means just divide the equation by x3. So what we will get is yti equal time divided by x3i. That means per capita terms we are considering consumption per capita, consumption expenditure per capita equals to beta 1 times 1 by x3t plus beta 2 x2t by x3t, that means GDP per capita, plus beta 3 now becomes the intercept term plus ut x3t. Such a transformation may reduce collinearity in the original variables. Clear? So what are the remedial measures that we have studied? The first one is if we have some prior information, we can use it, like beta 3 equals to 0.10 beta 2. If we have data, we can just compile them to get the pooling data. Thus, the simplest way to drop some variables, and dropping some variables can lead to specification error, specification bias. The fourth one is very important. If we transform those variables, okay, by first difference, or we can do on a ratio basis. The last one is addition of new data. Add some more data. Since multicollinearity is a simple sample feature, it is possible that in another sample involving the same variables, collinearity may not be so serious as in the first sample. For example, if you have taken the data from South Kolkata and if you take data from North Kolkata, there can be a huge differences in those two localities, and that can lead to some other kind of problem, right? So there, if in South Kolkata there is a serious problem of multicollinearity, that should not be the case in North Kolkata as well. So sometimes simply increasing the size of sample may attenuate the collinearity problem. For example, in the three variable model, as we know that variance of beta 2 hat equals to sigma square by summation x2 I square by times 1 minus r square 2 3. If we increase the sample size, summation of x2 I square will generally increase. Therefore, for any given r square 2 3, the variance of beta 2 hat will decrease, thus decreasing the standard error, which will enable us to estimate beta 2 more precisely. Other methods of remedying multicollinearity is a kind of factor analysis and principal component. These techniques you will study in the like in the later period, actually in the master's level. This factor analysis and principal component, they uh, uh, these are the things by which we can solve the multicollinearity problem. So multivariate statistical techniques such as factor analysis and principal component, or techniques such as ridge regressions, are often employed to solve the problem of multicollinearity. Unfortunately, these techniques are beyond the scope of this chapter, for they cannot be discussed competently without resorting to matrix algebra. If we do this using the matrix algebra, then we can easily do the factor analysis and principal component, I think. Okay, but this is not required in undergraduate part. So okay, so this is basically multicollinearity. Thank you.